Welcome to this talk about online learning of deeper variable ordering heuristics for constraint optimization. Test. Okay. Welcome to this talk about online learning of deeper variable ordering heuristics for constraint optimization. This work is by Floris, Doolaard and Yorke-Smith. In 2020 and 2021, we've heard a lot about shots. This paper is about one-shot learning of optimization heuristics. Nothing medical here. The goal is to learn heuristics for solving a combinatorial optimization problem where we have no prior data. This is one-shot learning. We're going to learn instance-specific variable orderings for constraint optimization problems. What that means is we're going to learn a custom variable ordering for a given instance of a COP. But remember, we have no prior data. We've not seen this instance before or other instances like it. As far as we know, this is a new thing. The idea is we have a probe phase, a learning from that data gathered from the probing, and then thirdly, a solving phase. So we're going to probe the problem, learn from that, and then use what we've learned to help us solve. In one slide, this is what the framework looks like. In a few minutes, I'll explain what all these parts are. Key things to note already are we're using Minizinc as the input language. We're going to use G-code as our constraint solver for all the experiments. We're going to do the learning using scikit-learn. And there's several parts you can see there, step 1, 2, and 3. We'll come back to those. Those are the 3 parts of our approach. The inspiration for this paper comes from an earlier work from CPAIOR 2015 by Chu and Stuckey, where they learned value ordering heuristics for constraint problems. They did value ordering heuristics. Well, we thought, why don't we do variable ordering heuristics? And there are some differences between our approaches, but this is where the inspiration comes from. On the left, I've depicted a search tree. We're at node A of the search tree, and its children are P, Q, and B. You can think of this as the choice of variable to branch on next. And what we branch on will depend on how quickly we either find a solution or we find a no-good. Now, normally at node A, we run some variable ordering heuristic, such as maybe smallest, or any of the other standard Minizinc heuristics. But what if, just what if, we could do what we call a deepification process? Rather than running a standard classical shallow variable ordering heuristic, what if by some process of deepification, we could have a heuristic which would do more look ahead? And this is the idea. Rather than doing the standard heuristics, which look ahead maybe 0 levels or maybe 1 level in the tree usually, what if we could look ahead as many levels as we wanted in the search tree? So here on the right, the heuristic would tell us already at node A that we should choose B, and because B is going to lead us to C, which will lead us to D, which will lead us to a solution. Of course, nothing comes for free, and we can't have knowledge of the future, that is future of the search tree, without doing some work. So the question is, how do we do this deepification? And the answer is, we're going to do a probing phase, and then you use machine learning to generalize what we found in the probing phase to give us an approximation of a deep variable ordering heuristic. So if you will, on the left is our input variable ordering heuristic, such as smallest, and through this deepification process, we get a deep smallest variable ordering heuristic, which is able to do more look ahead. Let's go through the idea. So here again is our search tree. For the sake of argument, suppose there's 3 variables, x, y, and z, and we're going to pick the variable with a minimum score. So we have a score function from our input default heuristic, say smallest. And we want to look ahead in this example a depth of 2, d equals 2. Okay, so we're at node A in the search tree. Now we can run our heuristic, our regular heuristic, and that's going to give us scores. It's going to give us scores for the variables x, y, and z. And you see I've decoupled the names of the search nodes from the names of the variables. So if we run the given heuristic on variable x, it scores 1, y scores 2, and z scores 3. Okay. Now, if we proceed with search, if we were to choose x, let's say we find no good. If we were to choose y, well again, we're going to find some no goods. But notice when we move to node q, having chosen variable y, we then have to use the heuristic again, and that's going to give us scores at the next level in the tree. And the best choice was to go to node B. That's choose z first, and then y, and then x in that order, and that finds a solution. Okay. It's just an example, it's just constructed. Now, the idea of constructing the deep heuristic, the deep version of the given heuristic, is to generalize the score function. It works like this. So let's look at node Q. So if we were to go here, we get a heuristic score of, well, the score of going to the node, plus then the scores of the children of the node. And we take the average. Here there's 3 nodes. We score 2 from going from A to Q, we score 3 from going from Q to R, and 3 from going from Q to S. 2 plus 3 plus 3 over 3 nodes gives us that score. Notice we've had to use information from the future of the search tree in order to compute this score. Well, what if instead we went this way? The heuristic score of going from A to B, well, again, it's going to be 3, that's A to B, and then it's 1 from B to S and 2 from B to C. We take the average, 3 plus 1 plus 2, that gives us a score of 2. Just another example. Supposing we're going from B to C, well, the score of the regular heuristic is 2 from B to C, and then 1 from C to D. That will give us a score of 1.5. So you see what's happening here. We're using the input heuristic, the regular variable ordering heuristic, the classical heuristic, and we're running the heuristic repeatedly, and then combining that into a deep heuristic score. In order to do this, we need information about the future, and that's where the learning is going to come in, as I'll explain to you next. So here's our framework overview again, and now I'm going to go through it step by step. The input is a problem modeled in Minizinc, and we made a custom search annotation in Minizinc. We called it heuristic search, and then you can just do solve heuristic search. For example, in this fragment here, row is the array of variables we want to search. So Minizinc is very easy. All you do is just specify this new annotation. Okay, what happens under the bonnet? Well, Minizinc, if you're familiar with it, compiles to FlatZinc, which then goes to a solver. As I said, we're going to use G-code for all our experiments. G-code is a well-known constraint programming solver, open source. Now, when G-code receives the compiled Minizinc and it sees this annotation, well, we added into Minizinc some custom code which will then call our modified search procedure. So we had to do some additions to G-code to do that. What happens? Well, step 1. Remember, our step has approach has 3 steps, 3 phases. The first is probing. You can see it there. What we do is we take the input problem and we randomly choose values. We're going to do random search, random variables, random values. And we're going to store what we find in some tree structure. And we're going to continue until we say stop. We hold up a stop sign. That could be based on time for probing. We might give it a few seconds. It could be based on number of nodes or another condition. Okay, that's going to give us some data about variable and value choices. We might get lucky and come across a solution. That's great. We might come across some no-goods. That's also useful information. Right now, we don't use any of that. We just run the search to collect If you find a solution, okay, that we can record, but we don't do any extra inference. Step 1, we collect data through probing. What we're going to do is use this in a restart-based search, and I'll explain more later. And in fact, we do restarting as part of the probing, because we want to randomly sample as much of the search tree as we can, hence random variables and values, and then some restarts to try and give us a diverse data set. Okay, so we have our data. What we're going to do now is to compute labels. Given we know parts of the search tree, we compute the deep heuristic scores. These are the scores I showed you on the previous slides. And that means we're going to do iteration over the probe tree. We keep calling the score function of the input, the classical variable ordering heuristic, and we use that to give us scores for the deep version of the heuristic. So smallest will become deep smallest, etc. Okay. Now, how do we do the deepification? Remember, we only know the deep heuristic score over the little bits of the search tree that we've done our probing. We're going to use machine learning in order to generalize what we found into some approximate function. So we're going to choose values based on the node score, and we're going to cache the predictions of our machine learner. The details of how we do this are in the paper. The key thing to know is that we're going to use a random forest regression. We tried several learning algorithms. What this means in practice is that G-code is going to call Python, and we're going to run scikit-learn to do some learning. Then, in the main search phase, when we want to call our new deep heuristic, what that means is we make a call to the learned model, the learned random forest in this case, and we ask, please give us the score here. As I said, we cache to reduce the number of calls that we make. So that's the framework. You'll find all the details in the paper. I want to mention a little more about how we do our search. So when it comes to the heuristic search, the big green box on the previous page, that's phase 3 of our approach, the probing, the learning, and then the main search. We also do restarts in the main search. And in fact, it's something a little more subtle than this. We take our search time and we split it into what we call a number of jobs. And each job not only does a restart within the search, like your solver might normally do, we in fact restart the whole procedure. Probing, learning, so fitting the ML model, and then search, just the regular search of G-code, for example. Why do we do this? Well, the idea is to, again, invoke randomness. Remember, the probing is usually very time limited, and we have then the approximation because of the machine learning. So if you will, we do these restarts in order to exploit the randomness we have from the probing and try and take some kind of average of the search process. Now, in our current implementation, we don't share any information between jobs. So job 1 on the left there shares nothing with job 2. We could share the probing trees. We don't do anything. We just restart the whole thing. So what this means, if we have, say, 60 seconds of solving time, we might say, okay, we're going to do 6 jobs with them 10 seconds each, and each might get, say, 1 second to the probing, and then the machine learning model is quite quick. That's why we chose a random forest regression, and then about 9 seconds for the search. So 10 seconds for job 1, 10 for job 2, etc. We don't run jobs in parallel, although you could do that. There might be parallelization within the solver, so in the search box there, but our jobs just run sequentially. Essentially, we're just restarting the whole procedure. Okay, so there on the left is our framework. I also mentioned the restart-based search. Let's see if this works, this idea here. We'll try it on 3 variable ordering heuristics. We chose a sample of 3 of the ones available as using annotations: smallest, max regret, and anti-first fail. And we chose some constraint optimization problems from the mini-zinc benchmarks. We did RCPSP, Amaze, Evilshop, OpenStax. Again, just to take a sample of different types of problems. We're going to run our experiments, not for 60 seconds, but for 4 hours. But we're going to let each job in our research-based search run for 15 minutes. And we determined that number 15 from some preliminary experiments. It's not particularly optimized, it's a hyperparameter. As for the depth, the maximum depth we're going to do probing and deepification over is 25. And again, we did some preliminary experiments. And in fact, in the paper, you'll find we did some experiments looking at changing these parameters. So what if we changed the job time, make it bigger or smaller? Okay. Let me give you an overview of the results. So here on this slide, we see 3 graphs for the 3 different deepified heuristics. Deep smallest on the left, deep max regret in the middle, deep anti-first fail on the right. And within each graph, we have runtime on the vertical axis, and on the horizontal axis, we have the average over the 4 different problem classes. So for example, the bar all the way on the left is going to be the runtime for deep smallest on RCPSP. The blue bar is G-code. They're just regular, untouched G-code. We give as input the problem, we say go. The stacked bars is our approach. And here we split it into the 3 phases. So you can see on RCPSP with the smallest, we're actually slightly slower than average. That's not a win. And you can see the probing time, the machine learning time, and then the search time. Okay, so our search time is less, that's good, but we have to spend some time doing the training of the ML model, a little bit of time, and the probing takes some time, so overall we're slower. You'll see on the leftmost graph again, for Evilshop, we're a little bit quicker. For Amaze, we're slightly slower. For OpenStax, we're quite a bit quicker. The middle graph is deep max regret. And for this one, we're better on Evilshop, for example, but we're worse on Amaze, and the other 2 are pretty close. And the graphs on the right are deep anti-first fail. And for this, we're better on RCPSP, for example, and in fact, we're better on all 3 problem classes. So this gives some indication that our approach has some potential. Here I've shown the graph again, but here I've shown the error bars. So rather than splitting our approach into parts, I just made it just the green bar. So the graph is telling the same story as before, but here we're showing the error bars. So what's the variance? And what we see also is that there are some instances which timed out, that neither G-code nor our modified version of G-code with the deep heuristics, neither can solve within the time limit. So we see some of that. And we also see there's quite a bit of variation in our solving times. And that's due to this randomness of the probing we use. So we thought these results are promising. There's more to do, but they're promising. So to summarize, what are we doing? We're doing three things in order to solve in an online way unseen problems using custom variable ordering heuristics. Our 3 steps, all online, are probing, approximation of a deep heuristic using machine learning, and then leveraging that in a simple sequential restart-based search. The results, as we've seen, are promising. In the paper, you'll find more graphs and tables and so on. Some things we're still interested in doing. An ablation study, looking at the elements of our approach in more detail. And then adding variable and value ordering together. So in our work, we had a simple random value ordering, just to keep things constant across all the results. But actually, our approach could work for both together, variable and value ordering. Thank you for your attention.